So we're going to talk about behavior of components, and unfortunately, we'll talk about the components next week. These are some terms. Some of the stuff, well, hopefully you're familiar with all of these from the technician. Um, we'll talk about elementary charge a little bit next week, which is uh, either the charge on an electron or a proton. They're equal, but opposite. So protons and electrons attract one another, and protons repel other protons, and electrons repel other electrons. But the charge is how we get the electromotive force. So you have to have a charge between two elements, which generates the electrostatic field, and that's actually the force that will cause current to flow. Uh, we use this capital letter Q to represent charge, and it's the number of coulombs, named after a scientist, that are accumulated. And 1 coulomb turns out to be 6.24 times 10 to the 18th elementary charges. That's a lot of them, although they're very, very small. When we talk current, okay, what we're doing is representing the flow of a charge, and we do that in coulombs per second, which we call amperes. So if you had a 1 ampere current flow, you've got this 6.24 times 10 to the 18th charges moving every second. Like I said, the charge creates the force, and we call it electromotive force. And we usually represent it with E for electromotive, as opposed to V. We just use V to represent volts, which is the amount of force. We measure the force in volts. And resistance is the opposition to current flow. We measure that in ohms, and we use R to represent the resistance. Now, we'll also talk about in a little bit reactance. We also measure reactance in ohms because it's the opposition to current flow in frequency dependent devices like inductors and capacitors. So they behave differently than a resistor. A resistor is a linear device, and the Ohm's law applies. Ohm's law is a little bit different when we talk about reactance because we're talking about complex numbers. We use F typically for frequency, and we now call those hertz, named after old Heinrichs. It made more sense when it was cycles per second, but a long time ago they decided to change it. And then little c is the velocity of light in free space, or approximately 300 million meters per second. We use lambda to represent wavelength, and you'll see more of that when we talk about antennas. We already did R. We use L for inductance, which is representing the amount, or the ability to store energy in a magnetic field. Whereas capacitance, we use C, which represents the ability to store energy in an electrostatic field. So one device stores energy magnetically, and the other stores device electrostatically. And when we get to talking about resonance, when you have an inductor and capacitor in resonance, what you actually have, they're storing equivalent amounts of energy, and the energy just gets moved back and forth between the magnetic field and the electrostatic field. And that's resonance or oscillation. We use X to represent reactance because it's slightly different than pure resistance. And we use Z to represent impedance, which is the complex result of resistance plus reactance. And we'll talk about that more later. So we're going to talk about reactance, inductance, capacitance, impedance, and impedance matching first. So what is reactance? It's the opposition to the flow of alternating current caused by inductance and or capacitance. We measured in ohms. The formula for inductive reactance is X, we usually use X sub L, which is 2 pi F, again, like in the first one, times the value of inductance. If we do frequency in megahertz, we can do the inductance in micro henries. Otherwise, you would do them in hertz and henries. But it's in the real world, it's a lot easier to do megahertz and microhenries. Capacitive reactance is similar, except it's a reciprocal. So it's 1 over 2 pi times the frequency times the value of the capacitance. Again, we can do megahertz and microfarads as opposed to just hertz and farads. One thing to remember is inductive reactance increases with frequency. Capacitive reactance decreases with frequency. And that's why they're different than resistance. Resistance is the same regardless of frequency. So these are frequency variable resistances effectively. Any questions so far? Can't hear you.
Sorry about that. Yeah. I didn't want you hearing the cats while you were talking. Yes, I do. I see it. Can't say that I could repeat it right now. So,
Okay. You just need to understand the principle.
yes, I got it.
Although, yeah, and these two formulas.
Got it.
Okay.
Got them written.
And I tried to add some charts to kind of graphically explain reactance. We'll see how well they work. This is just a plot of reactance in ohms versus frequency in hertz. And you can see it's a linear. The slope of it depends on the frequency and the inductance. So the higher the frequency, the larger this angle. So it's going to have higher reactance. Or the larger inductance, it's also going to increase the angle, so it'll be higher inductance. So here I did a plot of a square wave, and we just called it frequency F. And I purposely said it was the width of it, of the pulse, was 10 tau. As I recall, we won't talk about tau in the general class, I don't think. Don't exactly remember, but that represents a time constant. It turns out that when you're charging an inductor or a capacitor, either charging up the magnetic field or charging up the electrostatic field, it charges up with this curve. And it takes 5 time constants for it to get up to 99%. And we use that a lot in electronics, where it'll go up to 56% in one time constant, and then it goes like 30 and on down to where it approaches the full charge. Uh, and the voltage goes up like that also. So what I'm trying to represent here is the current that's flowing uh, while we apply the voltage in the inductor. So assuming this is a um, fairly low frequency relative to the inductance, we're going to have enough time to completely charge up that inductor with the maximum magnetic field. And then when we take the voltage away, it's going to dissipate or try to dissipate the charge. So there's enough time for it to go back to where it was. In the case of an inductor, it tends to reverse polarity when it does that. So if we up the frequency, you can see now it doesn't have as much time to charge. So we actually have a little less area under the curve. And what I did, I think I did it on the previous one. Yeah. I plotted what the RMS value of this current would be. And you see it's up fairly high, close to the maximum. And we'll talk about RMS later today, where it's the value of an AC waveform that's equivalent to a DC waveform generating the same amount of power or heat. So when you talk about your wall socket at home, your 120 volts, that's 120 volts RMS. So it's equivalent to having 120 volt DC as far as the power is concerned. It's actually a much higher peak to peak voltage. So when we double the frequency, we have only half as much time to charge it. In this case, we're just getting to full charge. And the RMS is a little bit lower. I double the frequency again, and see now it's only partially charging. And when you look at the RMS, which is just flipping these negative portions up here and essentially calculating what the area under the curve is, you can see the RMS is dropping, has a less effective voltage or current, I should say. Now I'm going to go up 10 times. Boy, we're not charging much at all. And you see our RMS is way down, and the amount of and the current going through that inductor is very small. I'll go 20 times, and it's still there, but extremely small. That's how an inductor works with an alternating current. And if you were to calculate what the equivalent resistance would be with the applied voltage to give you the same amount of current, you'd come up with the amount of reactance in ohms. So it's the effective resistance at that frequency for that amount of inductance. Does that make sense?
Those are good graphs.
All right, well, we'll do the same thing with capacitance. And like I said, capacitance decreases with frequency, or excuse me, capacitive reactance decreases with frequency, whereas inductive increased, so the current decreased. In this case, the current's going to increase as we increase frequency. Because it's a reciprocal, it's not a straight line curve. It's 1 over 2 pi FC. So we'll do the same thing. Uh, we'll use the same starting frequency, and you'll see we have an extremely high initial current because a capacitor that doesn't have any charge looks like a short circuit, like an empty tank. So you have a high current initially, and as it starts charging up, the current drops. When the voltage goes away, uh, or goes back to zero, we start discharging it. So you have a high discharge current, and it drops till it gets back to zero. So when we double the frequency, in this case, we're still charging it, but our uh, RMS value came up a little bit. When I go 4 times, uh, I have a maybe double the RMS. When I go 10 times, uh, and these are my best approximations. I didn't actually calculate this. You can see we're getting up to where most of the current uh, that the capacitor is capable of passing is going through it. And at 20 times, whatever that initial frequency was, we're almost the maximum current. So capacitors will pass high frequencies, they will block low frequencies. And inductors do the opposite. They pass low frequencies and block high frequencies. That's the basic thing you need to understand about inductors and capacitors.
Would you say that one more time, please?
Okay. Capacitors uh, try to block low frequencies and pass high frequencies. Inductors pass low frequencies and block high frequencies.
Okay. Okay. Thanks.
And that's how we use them to make filters so that we can pass or block certain frequencies by the way we connect up in the values of inductors and capacitors. I found this chart, it's a little busy, but it's got a lot of information. Um, the one in the middle is just your standard, you see a lot plotting both uh, inductive reactance and capacitive reactance. The one thing to note, and we'll talk about that in a little bit, is where they cross. And at that point, the inductive reactance and the capacitive reactances are equal. It also means that both the inductor and the capacitor are able to store equal amounts of energy. So that's the resonant point where they can transfer the energy back and forth between the two without losing any or having any leftover, I should say. Uh, so that's an important thing to remember. Resonance is the point at which the inductive and capacitive reactances cancel each other out. So when we look at the impedance equation, which is R plus JX, X is going to be 0. So the impedance is going to be R at resonance. And we'll talk more about that. Over on the left is some information about a capacitor. If I recall, technician covered what a capacitor was, right? Two plates separated by some dielectric. And the capacitance is going to be equal to the area of the plates and the separation and what's in between them. So those three things determine the value of capacitance. And that's also how much energy it can store. Uh, And these are just kind of the same thing, showing the reactance plot, and that at low frequencies, your reactance is large or high and small at high frequencies. Same thing over here for inductors, where it's a coil of wire. It has a low reactance at low frequencies and a high reactance at high frequencies. And it's a linear plot as opposed to the capacitor, which is a reciprocal plot. So that's why it's a curve. Um, oh, so I mentioned resonance. So if we have an LC series resonant circuit where I have a resistor, inductor, and capacitor all in series, when the inductive and capacitive reactances are equal, I'm only going to see the resistance in that circuit. So L and C effectively disappear from the circuit at the frequency at which it becomes resonant, where X sub L and X sub C cancel out. So if I look at the impedance equation, the general one, it's going to be the resistance in the circuit, series resistance plus J, and I'll talk about that a little later. It makes this a complex vector. So we're not going to go into the weeds too much on this. It's just we represent it as at 90 degrees or orthogonal to the real axis. So this is essentially an imaginary number in that it can't do any work uh, or create heat. So it's the combination of omega L, and remember I said omega is a shorthand for 2 pi f, minus 1 over omega C. So when they're equal, that term becomes 0, and all you're left with is the impedance Z is equal to the resistance R, which is only true when the reactances are equal, when you have a resonant series circuit.
And the practical use of this is in tuning your transceiver,
Well, practical
tuning
use
the antenna.
is oscillators, antennas, filters.
Okay.
All of those things depend on resonant circuits.
Okay.
And in the case of the series circuit, when we're some frequency below resonance, you're going to have R plus some effective X value. So it's going to be a high impedance. As you approach resonance, it becomes lower and lower until it's equal to whatever R is. And if R is low, your impedance is going to be low. As you keep increasing frequency, your reactance starts going up again because X sub L starts becoming larger than X sub C. So you see a curve where you have a dip at resonance and then it goes back up. If we look at a parallel resonant circuit where you have the resistor, inductor, and capacitor all in series, the impedance equation is a little different. And we'll talk about how we do parallel resistors, capacitors, inductors in a bit, which is what this is how you calculate parallel impedances. So when we have resonance, when it's a parallel circuit, Again, the L and C are going to cancel out, and you're going to be left with the R value. Now, in most cases, this R is going to be high. Otherwise, it would really lower what we call the Q of the circuit. So typically in a parallel circuit, this resistance, if it's there at all, is going to be normally a very high resistance. So in this case, you're going to go from a low impedance at a low frequency up to the maximum impedance at resonance, and then back down to a low impedance. Because if you look at the circuit, if we're down at a very low frequency, what's the inductor going to do? It's going to pass that current. It's going to be, you know, very low opposition to current. The capacitor is going to block the current, so it's effectively not going to be there at very low frequencies. When I get up above resonance at high frequencies, the inductor becomes an extremely high value, so it's effectively not there in the circuit, and the capacitor is starting to conduct current. So it becomes a low impedance in parallel with the R value. Here's a couple plots. So this one, we're plotting impedance of the series circuit versus frequency. And you can see we start off high and we get down to a minimum at resonance, and then we go back up. Now, the shape of this is going to be dependent on a bunch of things like parasitic capacitances and things like that, and the amount of resistance, which is going to affect the Q. So the higher that what we call the Q of the circuit, in other words, the smaller the series resistance in this case, the higher the Q, and it's going to be a much sharper curve where it's going to stay high and come down to almost a point and go back up. When we look at the parallel circuit, we start off low, we go high at resonance, and then we go back low. And again, depending on the Q of the circuit, depends on how sharp this curve is going to be. Typically for a resonant parallel circuit like this, it would normally have a fairly high Q, and you see a very sharp peak instead of this broad one they're showing here. Any questions on those?
Well, like I said, it's a lot to absorb.
Just remember, capacitors pass high frequencies, inductors pass low
That's
frequencies.
frequencies.
Okay, so we'll talk about impedance, uh, which is, like I said, a complex number, and it's the opposition to the flow of current, like a resistor, except in an AC circuit. So it's the combination of the resistance in the circuit plus the reactance. And the reactance, if it's capacitive, is going to be a negative value. That's why when they're equal, they cancel out, because inductive is positive and capacitive is negative. So if they were both 1,000 ohms, you'd have plus 1,000 and minus 1,000. If you
Is that
wonder
why
where the
on the bottom you have inductive impedance? Is
right,
that right? Okay, never mind. I'm sorry. I read it wrong. Okay.
oh yeah, that's X sub L and X
Mhm.
sub C. If you wonder what the J was,
It's instead of I because we use I already. I remember that.
okay, and remember I is the square root of -1.
I didn't remember that.
Because nobody could figure out what the square root of minus 1 was. So it's plus or minus I, which mathematicians use. Since we use I for current, we had to pick a different letter.
Right.
Okay, so where does J come in? Okay, if we plot the impedance of this inductor versus frequency, um, and this is the, well, it's both polar and Cartesian. So my, let me see. I didn't create this chart, so make sure. If we plot it on a Cartesian scale, we're going to plot the real amount of resistance that's in the circuit plus the reactance. In this case, for the inductor, it's going to be the capacitive reactance. And we plot that on the vertical or imaginary axis. So that's where the J comes in. This is our J axis. And this is our real axis. So we're plotting real versus imaginary. It's imaginary because, like I said before, it doesn't do any work. There's no power. You can have energy stored, but there's no energy dissipated or converted. Any power on the real axis will generate heat. The imaginary axis won't generate any heat with current flow. When I do the same thing for capacitor, we plot it as a negative J. So we plot it down here. So we'd plot the real plus the length where the reactance is and draw that vector. And usually when we talk about the impedance vector, we talk about the magnitude of it, which is what the two bars represent. As opposed to the complex value, it's the length of the vector. And if you remember from high school math, uh, um, whatchamacallit's formula, which is the square root of the sum of the squares.
I remember, yeah.
Okay,
But
that's
been a
what we're
long
doing.
time. Yeah.
The length of the hypotenuse is equal, the square of the hypotenuse, okay, is equal to the square of the two sides. Okay,
Pythagorean theorem.
so z would be equal to the square root of the sum of the sides.
Right.
Sometimes you'll see it plotted in what we call polar coordinates, where you're just plotting the length of it versus the angle and not plotting the real part of the axis. You'll just see a vector at some angle. And that's the polar form of it, which you don't really need to remember this term. And the angle you can do on your calculator, which is the arctangent of the ratio of the two, the reactance over the resistance. So, and we do the same thing over here for C, okay? We can represent it either Cartesian or polar. And the magnitude of the impedance is going to be the square root of the sum of the real squared plus imaginary squared. Okay, so we'll throw another term in. And this is there's only one question on this, as I recall. Uh, the reciprocal of impedance we call admittance. And instead of using Z, we use Y. We're going to wind up using most of the letters of the alphabet before we're done. And instead of measuring in ohms like we do resistance and impedance, we measure it in something called Siemens, named after some guy. I don't exactly remember what he did. So uh, Y is going to be equal to the reciprocal of impedance, or 1 over the impedance value. And the Siemens is going to be the reciprocal of an ohm. So the way I like to remember it is impedance impedes current flow. Admittance admits current flow. And sometimes you won't get into it, but in designing amplifiers and things, sometimes it's easier to work with admittance than it is impedance, which is why the term comes up. But the only thing really to remember is the reciprocal, and we represent it with Y. Okay, we also have impedance matching. So what does that mean? We want to match the source impedance to the load impedance so that you can get the maximum amount of power transferred from the source to the load. Typically, the load is going to be your antenna and the source is going to be your transmitter. And you'll have some matching device. It could be a built-in antenna tuner, which is a matching device, not a tuner, or an external one. And we have essentially 3 ways of doing matching. We can use a transformer. Uh, and again, this is one of these where we haven't covered uh, impedance ratio with transformers. We will in the next group, where it turns out it's the square of the turns ratio as opposed to just the ratio. Or we can use an LC network of resistors and capacitors configured as a pi or a T. Or we can use a quarter wave length of transmission line. So the main thing to remember is you can use all 3 of these methods for matching. Here's an example of using a transformer for matching. So our transmitter is connected into this transformer at one end of the coil, and the antenna is connected to a different one. It's kind of what we call an auto transformer, and it's going to give us a impedance change from the 50 ohms coming in to some higher value for the antenna. And these taps are on here, so you can pick one of those depending on what ratio you want to get. And it depends on your antenna. You can use the LC network, typically a pi or a T. This is what we call a pi network because it resembles the symbol pi. So you have 2 adjustable capacitors and an adjustable inductor. So on the antenna, quote, tuner, if it's a manual one, you'll have these 3 knobs and you adjust them to get the right impedance match. And you watch your SWR, or in the case of power amplifier, you watch the load and plate current. Or you can use a quarter wave transmission line. Sometimes you'll see that, you don't see this often, but it turns out that, let's say ZI was 50 ohms and your Z load was 100 ohms. If I insert a length of 75 ohm transmission line, that's a quarter wavelength long at the frequency I'm operating at. Per this formula, the impedance that it has will be B75. It will almost magically give you an impedance match from the 50 to the 100. It's not exact, but it's close enough. So it's a very easy way to do impedance matching. So instead of having a 2-to-1 SWR, you can get down to almost a 1-to-1. Any questions on those? Just remember there's 3 ways.
Mm-hmm.
When I said we want maximum power efficiency, if I plot source resistance and load resistance, at the point where they're equal is where I'm going to have my maximum power. It's only going to be 50% efficient. So if this was 50 ohms and this was 50 ohms, and they're at this point, I've lost half of my power in the transmitter to get half of the power to the antenna. The best you're going to do. That's just a fact of physics. So remember that reactance is the opposition to AC current flow in inductors and capacitors, that inductive reactance increases with frequency, capacitive reactance decreases with frequency. Resonance is where the inductive and capacitive reactances are equal and opposite. Remember, they have different signs. Inductive is positive, capacitive is negative. In a series LC circuit, it has a low impedance at resonance. A parallel will have a high impedance at resonance. Remember, they're opposite. And the formula for resonance, which if you do some simple algebra and you set 2 pi fl equal to 1 over 2 pi fc, you can manipulate it for f and you come out with 1 over 2 pi times the square root of LC. So if you need to find out what the resonant frequency is and you know the L and C values, you just use that simple formula. Or if you're familiar with doing algebra, you can easily recreate it. We said impedance was the opposition to AC current flow represented by Z, and it's a vector sum of the resistance and the reactance. Unless we just talk about the magnitude, and that's where we put the bars, we're saying it's no longer a vector, it's the scalar value of the hypotenuse or the length of the vector. Reciprocal is, admittance was the reciprocal of impedance, and we use Y instead of Z. Impedance matching was just matching source to load by using transformers, networks, or transmission line stubs. And the purpose is for maximum power transfer. So let's try a question.
Let me get my notes going.
You won't have notes on the test.
I know, but it ain't the test.
Okay. All right. So let me get this thing out of the way here. Well, I can't. Maybe you don't see it. What happens when inductive and capacitive reactance are equal in a series LC circuit?
When they're equal,
When they're equal and opposite.
then the impedance is low, is what you said. So, Charlie.
Very good.
Oh, all right.
What is reactance?
So react is the opposition to flow of opposition
Which one?
of alternating current caused by inductance and capacitance. So I'm going to go with capacitance, inductance, Bravo.
Bravo. All right. Which of the following, and I can't read it,
Causes opposition to the flow of alternating current in an inductor.
inductor.
Inductor causes alternating current and reactance. That's what we talked about, the delta.
Which of the following causes opposition to the flow of alternating current in a capacitor?
Isn't that the same thing?
Yep, same
Reactance?
thing.
Yeah. Okay.
How does an inductor react to AC or alternating current?
The frequency inductor, um, an inductor reactance should increase. Reactance should increase.
All right.
So delta. Okay.
How does a capacitor react to AC?
Frequency of the AC decreases, reactance decreases. So reactance to alpha or delta, alpha
What's the term for the inverse of impedance?
should be admittance because that admits the
Right.
uh, current flow. What is the term for it? So it's admittance, delta.
Okay. What is impedance?
Impedance
Oh,
is,
this is what I it was on the chart and I didn't mention it.
I don't know. Impedance and
It's like Ohm's law.
so it's the
You remember
ratio.
Ohm's law?
Yes.
What is
I,
resistance?
yeah.
What's the ratio? Is the ratio of what?
Voltage to current. So voltage to current here. The
Right.
ratio of voltage to current.
It
Sheesh.
turns out
I
it's the
need some
same,
help
except
here on this.
the only difference is you're dealing with complex numbers
Yeah,
as
to get the
opposed
math
to when
right.
we're doing Ohm's law, E over I are uh, real numbers,
Okay. But voltage to current,
but it's
yes.
still voltage to current.
Sure.
What unit is used to measure reactance?
It's what you just said, ohms. So bravo, just resistance.
Which of the following devices can be used for impedance matching at radio frequencies?
Delta. Hot dog. Those are the three.
What letter is used to represent reactance?
The X, B, bravo.
What occurs in an LC circuit at resonance?
At resonance, then they cancel each other. So delta.
Oh, okay. I moved that one to the end. I didn't delete it, but
Oh, okay. Can we take a little break here?
certainly
Thank you. And you stop recording.
I'll try.